So we talk about expectation of a discrete random variable. So this random variable is capital X. So expectation of capital X is you sum up all the values which the random variable takes. So you first take all the values of the random variable and then you multiply it with the probability that the random variable takes on that particular value. So this will be more clear in an example. So say you have an example of a simple coin toss. So the sample space for a simple coin toss, say it's a fair coin toss, is just head and tail. So now you can define a random variable x1 on it. So x1 acting on head, say, is 1 and x1 acting on tail is 5. So this is a fair coin, so you know that probability of head is equal to probability of tail, which is half. So thus we can write that probability of x1 is equal to 1 is half and probability of x1 is equal to 5 is also half. So x1 is equal to 1 is this thing. x1 is equal to 1 and this is associated with head. So the probability of x1 is equal to 1 is same as probability of head because you're feeding in head here. So you get this as probability of x1 is equal to 1. Similarly, x1 is equal to 5 is right here. So probability of x1 is equal to 5 is equal to probability of tail, which is also half. So now we just use this formula right here. So the random variable takes two values, 1 and 5. So you first write down the values it takes. It takes value 1, it takes value 5. So you have written down these values small x. This is multiplied by probability of x is equal to small x. So this 1 is multiplied with, so this is nothing but probability of x1 is equal to 1. And this is nothing but probability of x1 is equal to 5. So you multiply 1 with probability of x1 is equal to 1. You multiply 5 with probability of x1 is equal to 5. So another example. So say capital X is the random variable which is the outcome of the roll of a die. So once you roll a die, the sample space is you could roll 1 or 2 or 3 or 4 or 5 or 6. So more accurately we should say that x is the identity function on the sample space. So basically it means that x acting on 1 is 1, x acting on 2 is 2, x acting on 3, so x acting on 2 is 2, x acting on 3 is 3 and so on. So that you can also call x is the random variable which is the outcome of the roll of a die. But more precisely we should always remember that the random variable is a function on the sample space, and in this case x is the identity function on the sample space. So probability that x is equal to 1 is same as probability that x is equal to 2 is same as probability that x is equal to 3, same as probability of x is equal to 4, x is equal to 5, x is equal to 6 is 1 by 6. So probability of rolling a 1 or rolling a 2 or rolling a 3 or rolling a 4 or rolling a 5 or rolling a 6 is 1 by 6. So this is a fair die. So there is equal probability that you could have rolled any of these 6 numbers. So rolling one of these numbers is 1 by 6. So expectation is, again use this formula. So there are 6 possible values which the random variable can take. So you have 1, 2, 3, 4, 5 and 6, and then you multiply 1 with, so this is nothing but probability of x equals to 1, this is probability of x equals to 2, so this is probability of x equals to 3 and so on. So 1 multiplied by probability of x equals to 1, 2 multiplied by probability of x equals to 2, 3 multiplied by probability of x equals to 3. So going on, 4 multiplied by probability of x equals to 4 plus 5 times probability of x equals to 5 plus 6 times probability of x equals to 6. So basically all these plus signs are this summation, and again basically are following x times probability of capital X is equal to small x. Now you could have another random variable y on the same sample space of rolling a die. So omega is again the same sample space 1, 2, 3, 4, 5 and 6. And now this random variable y is the square of the input. So omega is right here. Omega is 1, 2, 3, 4, 5 and 6. And y is square of the input. So that is y of 1 is 1 square, that is 1. Y of 2 is 2 square, that is 4. Y of 3 is 3 square, that is 9. Y of 4, 4 square, that is 16. And now probability that y takes the value 1 is 1 by 6. Probability that y takes value 4 is also 1 by 6. Probability that y takes value 9 is 1 by 6. Probability that y takes value 16 is 1 by 6, and so on, precisely because probability that y takes value 1, this is associated with rolling a 1 because y is acting on 1. Here y is acting on 2, so probability that y is equal to 4 is rolling a 2, which is 1 by 6. Probability that y is equal to 9, so y is equal to 9, so this y of 3 is equal to 9, is probability of rolling a 3, this input right here, which is 1 by 6. So probability that y is 16, that y takes value 16, so this is y takes value 16, the input is 4, so the probability is associated with this input number that is in the sample space. So the probability here is again 1 by 6. Probability that y is 25, so y acts on 5 to give you 25. So probability that y is equal to 25 is probability of getting a 5, which is again 1 by 6. Then the final one is y acting on 6 gives you 36. So probability that y is equal to 36 is same as the probability of rolling a 6, and probability of rolling a 6 is 1 by 6. So expected value of y is, so you take the random variable here, so y takes the value 1, so this is 1 times probability that y is equal to 1. So this 1 by 6 is probability that y is equal to 1, plus y takes on value 4, it's taking on value 4, so you have 4 times probability that y takes value 4, which is 1 by 6, because y takes value 4 only if it takes an input as 2, and 2 is associated with rolling a 2 on a die, so probability of rolling a 2 is 1 by 6. So again, then you have 9 times 1 by 6, which is probability of y is equal to 9. So probability of y is equal to 9, this is right here, it is equal to rolling a 3, which is 1 by 6, and so on. So you add them up, you get 91 by 6.